Yeah, and so I was mentioning to a couple of the other folks who were joined earlier, the lectures are going to be recorded, and I'll put them up on Canvas and on YouTube. So you can feel free to go back and watch the lectures. And if you're not able to make it to the lecture, you can always watch the recorded video. I do encourage participation. I think that's the sort of best way to get the material out of the class. So definitely highly encourage showing up. All right, so for course logistics, we'll just get this out of the way. Grading. Yeah, so class participation. This was actually like more heavily weighted back when we had folks in person. It's a lot easier to do the participation. And so I'm going to be pretty flexible here. You can just kind of think of this as kind of free points, but again, you're going to get out of this class what you put into it. So I definitely encourage you to attend live if you can. Most of the grades are going to be focused on homeworks. So the bulk of the class grading. There's going to be a total of 4 homeworks. And yeah, and so they're going to be basically every other week, and kind of continuously throughout the quarter. And I do have a sort of 10% penalty per day. Okay, it says no exceptions. There might be some exceptions, but you do have to let me know ahead of time. And then lastly, final project is going to be worth a quarter of the grade. And there will be both a final report and a presentation. And so the grade will be divided evenly between those two. And I'll provide some more details now and a little bit more details down the line once it's time to sort of get started on the projects. In terms of the deadlines for the project, we're going to have class presentations basically on the last week. This should be, I need to double check, but this should be the week before finals. And so that week, you'll just do presentations to your fellow classmates, both on Monday and Wednesday. And then the final project should incorporate feedback that you get from your fellow students and from myself. And it'll be due at the end of finals week. Yeah, and that's about it that I'll talk about final projects for now, unless anyone has any questions. And also, if you don't want to just like chime in, you can also feel free to ask questions in chat. I'll try and keep an eye out on that. And if I'm ignoring a question, someone can just yell out that someone's asking a question in chat, and I'll go and read it. No questions. All right. So today we're just going to start with some basic concepts, a lot of the sort of overview of what we're going to be doing, and then thinking sort of from the fundamental building blocks of any particular energy system that we might be thinking about. Okay, so what is an energy system? So these are all the components related to production, conversion, delivery, and use of energy. It's a pretty sort of standard definition. This is drawn actually straight from the IPCC 5th assessment report. Hopefully all of you guys are familiar with this group. This is an international agency that basically releases these reports every couple of years on the sort of latest science on climate change, what's going on, what are the impacts, and also what's projected to happen as a result of anthropogenic and natural sources of climate change. And as you can imagine, the energy system plays a major role in the way that we assess how climate change is happening. And so a lot of the work in these assessment reports have to do with developing these nice cohesive energy systems and models that we're going to delve a bunch into. Okay, so what is energy modeling? So the goal is to understand energy consumption and associated impacts. So what are some of the things that we're interested in? So technology adoption, so you can think about all the sort of new technologies that are entering into energy, and in particular with my specialty is in transportation. So we think about things like electric vehicles, hydrogen vehicles, and how those are getting adopted, how different types of fuels are being consumed. And that can include thinking about the transitions between, you might think of 20th century prototypical fuels such as natural gas, gasoline, coal, and how those maybe transitioning towards things like hydrogen or biofuels. Economics plays a really important role in how systems work. And so costs and price and thinking about the finances and economics of particular systems is going to be an important component into the system. As I mentioned, energy systems have impacts on climate, and this is primarily through this vector of greenhouse gas emissions. But you should also note, right, that emissions associated with combustion of fuels, for example, also will lead to things like criteria pollutant emissions, which aren't necessarily directly leading to climate impacts, but may be leading to other types of impacts, such as those on health, on morbidity and mortality. And so these are a brief list of impacts that we often take an interest in. And most of the focus of the modeling in this course is going to be in this area, but it doesn't have to be confined to these impacts. There are a whole slew of other things to consider as well. And so in these sort of modeling approaches, you're going to be spanning many sort of disciplines, right? Even thinking about these impacts directly, we're already thinking about engineering aspects, environmental aspects, economic aspects, and so in this course, we're really going to be aiming for a lot more breadth in order to get a sort of systematic understanding of the way people approach modeling. And in terms of depth, I think this course will help to introduce a lot of the concepts, and that if any particular one type of tool or methodology really strikes your fancy, then I would definitely encourage you to explore that more, either sort of on your own with your advisor or in other courses in Davis. And of course, as those sort of topics come up, I'm happy to sort of provide guidance in sort of expanding knowledge in that area. Okay, and then I think one of the sort of unique things about this course that sort of differs from maybe other engineering and economics courses that you may take is that we're actually going to take a look at existing models and approaches that have been done in the scientific literature and in the sort of body of scientific knowledge, and how those actually have been directly applied to real policies. And so we're going to look at sort of at the end of class a whole bunch of policies that really spun out of or were heavily informed by scientific process. And you can see how modeling has led to the development of specific sort of types of policies. And so, when we talk about modeling, there are a couple different ways in which they can be applied to sort of a policy system. Oftentimes we're thinking about measuring impacts of policies as a sort of way of either providing sort of guidance to policymakers on what you think might happen, or to provide feedback on existing policies as a way of maybe updating the policy. And so there's going to be a lot of interaction between sort of the modeling world and the policy world, as we'll see. All right, so the course in general is going to build through these sort of 4 topics. The first one is going to be background, where we're going to talk a lot about pretty sort of basic knowledge in terms of energy engineering and technology. And that's sort of in order to make sure that as we get into sort of higher level aggregate models, that the stuff that's happening within the models isn't kind of just a black box for everyone, right? And so this means that, okay, well, I'll expect folks to know, how a natural gas, turbine works in principle, but maybe without all of the math. And so the first, I would say 2.5 weeks of class is going to be sort of just building basics and fundamentals. And then we're going to talk about tools, developing and understanding, once we get to sort of larger scale modeling, how, what sort of techniques are used in building system models. The third one is models. This is going to be looking at how the models are actually constructed, what models exist today, and we'll be able to sort of highlight systems and models that are prevalent in the existing literature. And this part has always been, I think, at least for me, maybe a little bit more challenging part of the course, because when we talk about, for example, like models that are being used in IPCC, those climate change assessment reports, a lot of those are sort of larger system-wide models that are too detailed to really sort of get your hands on them, because it would just take too long to learn. And so in a lot of this portion of the course, we'll be doing an overview of those types of models and how they work. But in terms of hands-on experience, a lot of the stuff that you guys will be playing with are going to be a little bit more simplified. And then lastly, as I was mentioning, the extension of the modeling to the policy world, how they applied, how they have informed our policy decisions. All right. Okay, and so building, understanding incrementally. So we're going to think about energy production in terms of technologies and fuels. I was going through some review papers and came across this sort of nice little diagram. I think this kind of highlights the background knowledge that we'll be getting into, and thinking about sort of the energy system as a whole. Really, it's all about going from a primary energy source, which is all the sort of fuel sources you see on the left, all the way to the final energy and consumption, which actually I'm not even going to call sort of the final stage. Really, what we want, right, is useful energy. And so when we think about like transportation, that's actually moving things from A to B, and then in terms of like industrial, commercial, residential, that's like the actual useful stuff that's happening for you, such as being able to watch a lecture on a computer. And so that sort of final step is maybe even downstream of what you're seeing here in this diagram. But we'll be talking about basically all of these individual components before we sort of link them all together. And so you'll have to look forward to sort of being able to understand each of these boxes individually. We'll be talking about all the traditional fuels that you were seeing in that sort of primary energy diagram. We'll talk about properties of the fuels, economics, resource generation and acquisition, implications of use. And so that relates to some of the impacts that we talked about before, including things like emissions, both for greenhouse gases and criteria pollutants. We'll also be talking about the technologies that use these fuels, power plants, engines, batteries, fuel cells, how do they work, what are the economics associated with them, and implications of use, how they've changed over time, and so on. Okay, so continuing to sort of building our understanding incrementally, energy consumption. So this is going to be talking about the end use of a lot of these points in the energy system and what sort of services they're going to be providing. And so, as I was pointing out in that previous diagram, so people aren't really interested in kilowatt hours of electricity or therms of natural gas or gallons of gasoline, which is actually one of these sort of metrics are probably the more common metrics that you see in energy modeling when we're talking about electricity consumption or heating or transportation. You're using some gallons of gasoline, but always keep in mind that at the end of the day, there are services that are being provided by these sort of end metrics. And so the final sort of useful energy, again, is something that's happening downstream of what we commonly think of as your sort of final metrics. Okay, examples of energy services. So things that these kilowatt hours or therms or gallons of gas can actually provide, right? So what are these? So these are things like lighting, right? Heating and cooling, mobility, electronic entertainment. These are the points of the system that often aren't going to be included in a lot of the modeling, even in the modeling that we do, but are considered really sort of the type of service that you want at the end of the day. Okay, integrating the energy system together. And so we think about how we go from production to consumption, all the steps in between, and then there's a whole sort of slew of energy efficiency things that we'll actually talk about today. That even if you were to sort of hand wave over sort of the nuances of the technology and the conversion that's actually happening at a high level, you can have a sort of nice understanding of the relationship between production and consumption through like a simplified metric for energy efficiency. Okay, and so all of this comes together and they result in some of those impacts that we're interested in. And so, the whole sort of point of putting this modeling system together is to focus on these specific impacts and other impacts that aren't included in this list. And of course, the relationship of public policy with the impacts of that system that can be sort of a feedback mechanism back into the system itself. And so if, for example, you want to reduce greenhouse gases, the impact of the system on greenhouse gas emissions, your public policy can be used to leverage the system itself to change those impacts. And so that's what this diagram is sort of showing. This is a sort of newer slide that I put in. And so when we think about sort of an energy system, the scale and resolution really matters in the way that you approach a modeling problem. And so a lot of what we're talking about in sort of the fundamental parts are with smaller sort of unit operations. And so this might be something like, okay, how does a specific power plant work? Or even something within the power plant, right? Like how does a specific turbine or the chemistry within the turbine work? And you sort of get sort of larger and larger scale from unit operation to plant to supply chain to your entire energy sector. And so as you go from sort of high resolution to sort of larger scales, we need to think about how the modeling sort of changes in what you need to sort of account for. Because if you were to, for example, try to simulate every unit and every individual plant everything operating within the plant at a economy-wide or sector-wide model, you're probably going to find that the model is going to be way too complex to operate efficiently, and that actually the type of detail that you're including in the sort of lower level operation is not useful in an aggregate model. And so those are the types of things that hopefully this course will sort of tune your brain to in terms of being able to identify, what the critical components are, what's necessary to include in the model. Okay, so this is, I think, a sort of nice breakpoint before we jump into kind of a basic introductory part of energy physics. And so why don't we take a quick like 5-minute break, and in the meantime, I'm happy to answer any questions that folks have. No questions yet. It's because I'm doing such an amazing job at teaching, right? How about a quick impromptu poll, kind of for me, or for my own edification? How many of you guys are coming more from, I guess I'll put it like a quantitative background, for more engineering-based backgrounds versus more qualitative backgrounds in terms of like policy oriented. Maybe just you guys can just put it in chat or something. It'll help me gauge the knowledge for the course. Cool, all right. Seems like we have more engineering. Everyone's an engineer, great. Okay, since we have so many engineers, this part will probably go a little bit faster, smoother for many of you. We're going to do a quick sort of basics energy physics recap. Okay, so we're talking about an energy transportation modeling course, and so we have to know what energy is fundamentally. It's the ability to perform work, which is basically means you can move something, right? Or heat an object. What are the main forms of energy? You've got kinetic, chemical, heat, electrical, electromagnetic, elastic, nuclear, and gravitational. So a bunch of these we're obviously not going to talk about very much in this course. But a few of these are going to be sort of critical to exploiting in order to make our energy system work. Okay, so a quick point of clarification. We'll be talking about, we'll often be talking about a concept known as energy conservation. And again, as a point of clarification, in physics, the conservation of energy means something fairly different from what we'll be referring to a lot in energy conservation. And so conservation of energy is a physics concept where energy can't be created or destroyed. You're merely converting it from one form to another, right? And so you go from like heat to kinetic energy to electric energy to back to heat energy. And this process describes, for example, a portion of the way our electricity system handles the transformation of energy, right? But energy conservation is a different sort of concept that's more rooted in sustainability, where we want to reduce energy usage in order to prevent wasting energy. And so we'll see how this particular topic relates through sort of the chain of energy conversions in a moment. But essentially the way that you can achieve energy conservation is through either service or activity reduction. And so those are, you know, those things that we were talking about in terms of like lighting, heating, cooling. If you can reduce the amount of energy that people use, you're promoting energy conservation. And then the other way is that, okay, even if the people are using the same amount of energy, if you can improve efficiency in the way that energy is transferred or transformed, then you are again achieving energy conservation. Okay, so one of the important concepts sort of related to the conservation of energy is exergy. And so exergy is our way of sort of thinking about useful energy, okay? So the maximum amount of work that can be derived from a system is sort of the description of exergy. So it is a measure of the quality of energy. And we have this sort of hierarchy of quality because the way in which we use the energy and are able to convert it to do the things that we want it to do kind of ranks differently in the types of energy. And so we think about, okay, if we're really thinking about the ability of energy to do work, then electricity and mechanical energy are sort of your most useful forms of energy. Much more so than chemical, and that even more so than heat. It's difficult to sort of directly to get a lot of that energy and conversion to the thing that we want without getting into lots of like efficiency losses. And so the important thing to remember about energy is that energy is always conserved, but exergy is destroyed as you convert from one type of form of energy to another. And so this diagram kind of shows some of the difference between energy and exergy. You can see that we think about in energy that sort of final state of useful energy in these terms, right? But really a lot of that is sort of low-grade heat that's not very useful. And so the quantity of exergy is quite a bit lower in your sort of bottom diagram compared to the top. Okay. How do we measure energy? So units of energy, where is it commonly used? What does it measure? Okay, so there are a whole bunch of different types of measurements of energy. You've got joules, you've got watt hours, British thermal units, and then you've also got calories and EVs. So the last one is more related to things sort of on the particle scale. And so we're not going to think about that at all. And calories are mainly with food. We'll talk about that a little bit, but the main things that we talk about when we think about an energy system are measured in joules, watt hours, and BTUs. Okay, so what is a joule? This is sort of the gold standard, right? So this is your SI unit for energy. And it's used in a wide variety of applications and fields, very commonly in energy systems. We'll talk about things in units of joules. Okay, and so what is the definition of a joule? A joule is defined as the energy required to heat 1 gram of water by 0.24 degrees Celsius, which is equivalent to the energy required to move an object of 1 kilogram, a distance of 1 meter at 1 meter per, at an acceleration rate of 1 meter per second squared. Yeah, and so that's an easy sort of way to remember it. It's all sort of in SI units in terms of being able to do this particular work on this object. And a lot of sort of everyday energy use and energy system use is sort of translated into joules that are all sort of relative to this particular definition, right? Okay, and so you've got something called a watt hour. So this is most commonly, and sort of come to think of it, is probably exclusively almost used in sort of electricity. And so this is the amount of energy used at a constant power rate over a period of time. So it is actually related to a joule. A watt hour is actually the number of joules used in a particular time period. So in this case, it's just multiplying by 1 hour. And so in an hour, a single watt will be using 3,600 joules, or 3.6 kilojoules. And so that's equivalent to 1 watt hour. And okay, so for those who aren't sort of familiar with the electricity system, this might be a little bit confusing, especially once we start talking about power and we're talking about watts. But basically the way to think about this is that when you have an appliance, for example, if you have a light bulb that uses a certain number of watts, it'll basically be telling you the amount of energy, that appliance is going to be using over a 1 hour period. And because things are measured that way, this has become a convention, and it's easy to talk about electricity in terms of watt hours. And so you can see here, this is a picture of an electricity meter, and it's telling you the energy consumption in kilowatt hours. And you could easily convert this to joules, right? You just need to multiply by some 3.6 factor. Yeah, and so in this particular example I'm showing, residential level electricity is often measured in kilowatt hours. When we start talking about things like power plants, we'll talk about electricity energy in units of megawatt hours or even gigawatt hours. Okay, and the last one in sort of common usage for energy modeling is British thermal units. So this is commonly used to measure energy content of fuels. So this is kind of the imperial version of a joule. So it's the amount of energy used to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So if you are not a fan of imperial metrics, this is going to be awful for you. But fuels are very often measured in these units. Fortunately, it's actually a fairly straightforward conversion, especially if you're doing like back of the envelope type of things. So 1 BTU is about 1,000 joules. And one of the sort of common reasons why this is still a thing is because it's really sort of nicely round for natural gas. So natural gas, 1,000 cubic feet of natural gas is almost exactly 1 MMBTU, which is 1 million BTUs, and that's about equivalent to 1 gigajoule. And because BTUs is like a really small unit, oftentimes there are a couple sort of abbreviations for larger scale units of BTUs. So a therm is 100,000 BTUs, and you can think of that as 100 cubic feet of natural gas. And then lastly, for some reason, the US likes to use these units to measure things on the economy-wide scale. And so the last thing that you'll kind of have to keep in mind is this unit called a quad, which is a quadrillion BTU, hence a quad. So that's 10 to the 15th BTUs. And so that's often used to describe energy consumption at large scale economies. Okay, actually one thing that I probably should mention, there's one more common usage of this. Let me just pull up my iPad so I can use my pen. Oh, it's definitely not working right now. All right, well, all right, so I'll sort of just describe this then. So a lot of power plants have this attribute called the heat rate. And a heat rate essentially describes the efficiency of a power plant. And so when we think about efficiency, and we'll talk about this today, it's kind of like energy in versus energy out. But for a power plant, we think about the energy in, which is the fuel, and the energy out, which is electricity. Here's where it gets a little bit confusing, is that a heat rate, even though we think of efficiency as kind of a unitless type of measure, a heat rate actually has units in that they describe the energy in units of BTUs and the energy out in terms of watt hours. So it's really common, for example, to have some kind of number for the heat rate, and then it'll be in units of MMBTU per megawatt hour or per gigawatt hour. And that tells you directly kind of, how much electricity can I get out of some amount of fuel input, right? And so it is the combination of the unit transformation from MMBTU to a megawatt hour or gigawatt hour, and the efficiency of the power plant. So that can be a little bit confusing, but as long as you remember, it's basically a translation between BTUs and watt hours, then hopefully that'll be kept straight in your minds. Okay. And the last one that we'll talk about is calories. And so these are most commonly used to measure energy content of foods. I'm sure all of you guys have seen this before, right? On your nutrition packs, how many calories. Okay, it's very similar to BTU, but in metric, it's the energy required to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmosphere. Yeah, so it's almost like the sort of direct metric translation of a joule. And 1 calorie is equal to 4.2 joules. One important thing to keep in mind is that when we talk about food calories, it's actually a little bit more confusing, because calories on food labels are actually kilocalories. And so on this nutrition fact thing that you see right here, this 25 calories is actually 25,000 calories. It's not just 100 joules worth of energy. It's actually 100,000 joules worth of energy. Okay. So let's do a quick sort of quiz. Not really a quiz, but can you guess the energy content of each of these items? So I kind of like to do these types of things every now and then. When we think about larger scale modeling, I like to get students in the habit of being able to think about things in terms of back of the envelope. In other words, like kind of get a nice sort of guess on the scale of things. And so for all of these, think about, don't try to guess like an exact number. Just think about this in terms of like order of magnitudes. And so, as an average meal, like 1 to 10 joules, 10 to 100 joules, 100 to 1,000 joules, right? And so in orders of magnitude, see if you can get these correctly. So normally I call on people, but I think that's a little more difficult with the online situation. So I'll just kind of take this slowly, and you guys can see how just follow along and see how close you are in terms of your guess, right? So an average meal, what's a quick way that I can think about doing this? Okay, well, I can maybe roughly guess the number of calories in a meal, and then I can do like a translation to joules or something. And so this is fairly straightforward. So, we think about like, what's the rule, like 2,000 calories a day. So that's, in terms of real calories, that's about 2 million calories. And then because the translation from calories to joules is less than a factor of 10, you're kind of in the same ballpark, right? So if you said, 100,000 to 1,000,000 joules, then you're kind of spot on. Okay, in a human body, it's 100 to 1,000 megajoules. Yeah, you can think of like, how many meals would it take to like build your body, right? Okay, so now we have a lump of coal, or I say 1 kilogram of coal. So this is between 10 to 100 megajoules, and we'll sort of get a little bit more specific on the actual energy content of coal once we get to that later on in the course. But as a sort of rough level of estimation, that's the amount of energy that you can get from a kilogram of coal. So, think about the energy density here as well, right? And so a human body, it has 10 times as much energy as a kilogram of coal, but it probably weighs, something like 50 times more, right? And so the energy density of a piece of coal is quite a bit higher than in the human body. Okay, so how does that compare, for example, to a gallon of gasoline? A gallon of gas is roughly 100,000 BTUs, which translates to about 100 megajoules. And so that is on the high end of that compared to coal, the 10 to 100. And so for a gallon of gasoline, it's actually quite a bit more energy dense than coal, but again, right, a gallon of gas is going to weigh more than a kilogram. Okay, so sunshine on a plot of 1 meter squared for 1 hour. And this is where I kind of like to point out the difficulty of solar power in sort of fighting incumbent technologies, right? So sunshine, if I were to collect sunshine for 1 hour, you're getting 10 times less energy than you get from a small sort of 1 kilogram piece of coal. And so there are some, this isn't to say anything about like economics or anything about the technology, other than to say, right, like the energy density of solar is quite a bit lower than a lot of these fossil fuels. Okay, EV batteries. So if you're familiar with electric vehicles, it's the size of the battery. In a Tesla is, for a longer range one, you're talking about on the order of 100 kilowatt hours. If you're sort of on the other end of the spectrum, if we're talking about like a Prius Prime, a smaller vehicle, you're sort of more closer to the sort of 10 kilowatt hour battery size, right? And so that's kind of the rough range of energy that's contained within a battery. And so you're talking about anywhere between 100 to 1,000 megajoules. Yeah, and so again, a nice little direct comparison, right? With a gallon of gasoline, think about the energy content there compared to an EV battery. How many gallons of gas would you need to have this sort of same amount of energy? And I know that this is not necessarily a fair comparison, right? Because the efficiency of converting the energy in a battery versus in a gallon of gas is going to be different. It's going to be very different. And we'll talk about that. But again, just to get you guys thinking at a high level about the energy content. So how much energy does a household use in one day? About 10 to 100 kilowatt hours, which translates to 100 to 1,000 megajoules. So roughly the way I like to think of it, I think the number that I've always had in my head is the power consumption for an average household is something like, in the US, is something like a kilowatt. And so you can translate that into energy pretty easily. Okay, just for fun, how much energy in a nuclear explosion? A lot, right? And so not too surprising. 10 to 100 petajoules, which is the equivalent of about 10 billion to 100 billion megajoules. Yeah, so you could provide, a nuclear explosion could in theory provide energy for what, 100 million houses for a day. US annual consumption, like I said, when you look this up, they're usually reported in these quad units. So that translates to about 100 exajoules. And so, the discrepancy in the units here is pretty vast. So I'm not going to try and compare them, but just to give you a rough sense of the energy consumption, it's about 100 exajoules in 1 year. And for the whole world, they don't report that in quads. It's in metric, so 100,000 terawatt hours, and so that's about 10 times higher than what you see in the US. Okay, and so quick breakdown of US energy consumption. So it's dominated by fossil fuels, so coal, natural gas, and petroleum. So this is actually, it's kind of like your most common form of solid, liquid, and gaseous fossil fuels. Petroleum is mainly going to be in transportation, and then natural gas and coal are primarily in electricity, although natural gas gets used for other sorts of things as well. You've got nuclear electric power, and then a small but growing amount of renewable energy. And so that 11% is sort of further separated out. Here you can see into a bunch of different renewable sources. The sort of vast majority of that for a long period of time has been hydroelectricity, but wind power has grown very quickly over the last 2 decades, and so is kind of on par with hydro, if not even exceeding it in some places. Okay. So that's talking about power or energy, and now we'll talk about power, which is the translation of energy over some amount of time. So it's the rate of doing work, and so you can think of it directly as all of the stuff that we talked about divided by some unit of time. And the only 2 units of power that we'll talk about are sort of watts and horsepower. Okay. So for watts, the SI unit of power is 1 joule per second. Okay. So this is most commonly used in electricity. We use this, for example, to describe capacities of power plants. So I'm sure most of you are familiar with the use of watts in like common household appliances, but even in other portions of your electricity system, it's very commonly used. So as an example, if a power plant has an installed capacity of 10 megawatts, what that means is that that power plant is able to produce up to 10 megawatts of instantaneous power. So 10 megawatts, again, translates to about 10 million joules per second. And so that power plant can produce 10 million joules of energy in 1 second. The other unit of power is horsepower. So this is most commonly used to describe power in engines and for mechanical power. So 1 horsepower is the equivalent of lifting 75 kilograms 1 meter in 1 second. Okay, that's kind of just the sort of conventional definition of a horsepower in metric. So weight, it gets better, right? We all obviously have to make this confusing, right? Because you actually have 2 different types of horsepower. There's an imperial version of horsepower, which is 745.7 watts. And you have a metric version of horsepower, which is 735.5 watts. I don't know why they do this. It's pretty silly to have 2 different ones, but there you have it. And in case any of you guys are wondering where this term comes from, we think about horses being able to do this work, but actually the peak production of a horse is not 1 horsepower, it's about 15 horsepower. So 1 horse can have more than 1 horsepower. Okay, let's do a similar type of exercise as before. Can you guess the power? So what is the energy rate, right? Or energy consumption rate for all of these different things? You've got light bulb, exercising human, all the way up to all of the power production worldwide. And see if you guys can guess at these before I talk about them. Okay, so a light bulb, this one should be pretty easy. Hopefully you guys have all some experience in this. So light bulbs, so I put 10 to 100 watts, right? These days, it's probably closer to 1 to 10. Back before you had a lot of LEDs and CFLs, you would have incandescents that are typically in the range of 75, 100, 150 watts for a light bulb. And nowadays, the light bulbs are so efficient that you can squeeze a lot more out of them, right? So I think a lot of the CFLs were sort of on the order of like 15 to 40 watts. And these days, your LEDs, where you're getting the same amount of luminescence, is what, something like 1 to 10 watts, maybe even lower than that. And so you've actually gotten a sort of order of magnitude improvement in energy efficiency for these. I should probably change this number to 1 to 10 to be more sort of up to date with the times. Okay, an exercising human, 50 to 150 watts. Yeah, and so that's really sort of peak capacity for an average human, and most people wouldn't be able to sustain like 150 watts, 200 watts for long periods of time. I don't know if you guys, you can YouTube this. There's a video of like a professional cyclist who powers a 350 watt toaster for like 30 seconds and he gets completely gassed. So yeah, these you're not going to get much higher sort of power output out of exercising humans. Which means we wouldn't be able to power a microwave, for example, which commonly operates at about a kilowatt. 1,000 watts is a fairly sort of standard power rating for a microwave. Okay, a solar panel. So a single solar panel, which, okay, this image is maybe a little bit deceptive because that's like multiple panels. But you're talking, so a single one of those rectangles is on the order of 300 watts. And so there are a couple different scales that we talk about when we think about solar panels. So residential ones, like you see in this picture, are going to be sort of on the order of a couple kilowatts because you've strung together a whole bunch of these solar panels together. For example, the one that I have on my roof is a 7 kilowatt system. And then you've got what's known as utility scale solar, which are the sort of big solar fields that you might see out in the desert. And those are kind of operating at the same capacity level as, you know, full scale power plants. And so you're talking about on the order of 100 to 1,000 megawatts. Okay, for a residential home, I gave this away earlier. It's about 1 kilowatt, at least in the US, sort of on average. Okay, next picture is a car engine. And so we can think about this translating from horsepower. If you got like a little dinky engine, you might be sort of on the 100 horsepower ish range. And then if you've got some really fancy multi-million-dollar car, you might have, you know, upwards of a couple hundred horsepower, maybe even as high as 1,000 horsepower. And that sort of on the order of magnitude scale sort of translates to about the same 100 to 1,000 kilowatts, right? Pretty interesting, actually, if you think about that relative to, you know, the consumption of a house, right? So your average car is consuming enough energy, or yeah, it is producing power at a rate that could power, you know, 100 homes to 1,000 homes on average. Okay, for wind turbines, you're talking about 1 to 3 megawatts, sort of for your typical wind turbine that you see out in on offshore facilities. The nearest one to Davis, if anyone has sort of passed by, is in Sweden, and there's a really big wind farm there that's got thousands of turbines. And so if you're familiar with those ones, so those are, most of those turbines are, I believe, 3 megawatt turbines. And they're quite big, right? So these blades are, you know, on the order of 100 yards long. And actually, 1 to 3 megawatts might be a good sort of characterization of offshore, sorry, onshore. So the ones on land, the ones that are offshore actually can actually be quite a bit bigger. You've got blades that span over, you know, 150 yards, and as single turbines can have capacities as high as 5 megawatts these days, which is kind of mind-boggling if you think about it. That's like a single turbine can power like 5,000 homes. Yeah, and so In aggregate, similar to solar panels, right? These things can produce as much power as full-scale fossil fuel power plants. So 100 to 1,000 megawatts. Okay, the next one is a natural gas plant, and these are very variable. They come in a wide variety of sizes. The sort of really absolute largest natural gas plants are producing on the order of a gigawatt of power, but most are usually a couple hundred megawatts. Coal plants are typically a little bit bigger. You've got quite a few coal plants that operate in the gigawatt range. So there's nothing really that's going to be sort of 10,000 megawatts. Again, this is sort of on the order of magnitude. But actually, when I was in grad school, I used to live by the largest coal plant in the US at the time. I think it's been retired since I graduated. But that power plant, I believe, was a 7 gigawatt coal system, which is like really quite astronomically large. But most coal plants are going to be sort of in the sort of gigawatt power range. And then lastly, you've got nuclear plants, and these ones are sort of similar in scale to the largest size coal plants that you see, and most of them are going to be really big. And we'll talk about sort of some of the fundamental reasons for why that is. But nuclear plants are typically going to be sort of the largest power producing plants that you see on average. There are some facilities of other types of fuels that actually exceed some of the largest nuclear plants, but those are kind of few and far between. Okay, how much power does California consume? This is a metric that I always like to have sort of easily accessible in my mind. So peak California power is about 50 gigawatts on average. It's quite a bit lower. You're usually sort of 10 to 20 gigawatts. But sort of on the hottest day of the whole year, where everyone's turning on their AC, California can reach power demand as high as 50 gigawatts. And it's important to think about these things, right? Because when we think about the electricity system, you need to build your system out to be able to meet demand at its peak, not sort of at its average. Otherwise, you're going to be running out of power and you're going to have lots of other sort of issues all the time. And so California has peak power at about 50 gigawatts. Okay, last one, total worldwide installed capacity. Yeah, this is not a metric that I commonly use, but just so you know, it's about 15,000 gigawatts. Alrighty. Okay, so as promised, the other sort of big topic that we'll talk about today is energy efficiency. So energy efficiency tries to reduce the amount of energy required to provide products and services. Okay, and so sort of the most generic physics version of thermal efficiency is where we think about what you get out of it versus what you sort of put into it. Okay, and so here you have a production of corn ethanol. And so out of 100 kilograms of corn, you get 11 gallons of ethanol output. So we translate our 100 kilograms to megajoules so that they are in the same units. And so as I was describing before, efficiency is very often in especially when we're thinking about like physics systems, a unitless measure. And so in order to make sure that you are, specifying the correct efficiency measure, oftentimes in these types of settings, you will translate it into the same unit before you do your conversion. And so here, this 100 kilogram of corn is being multiplied against the energy density of corn. So this is the amount of energy that's contained within the corn itself, 18 megajoules per kilogram. So I am putting in 1800 megajoules worth of kind of input energy. And the output is 11 gallons of ethanol, which has an energy density of 89 megajoules per gallon. And so that translates to a little under 1,000 megajoules. And so the sort of efficiency, the energy efficiency of this production process of going from corn to ethanol is about 54%, right? Which is your energy output, 979, divided by your energy input, 1800. And so a lot of that energy is lost in the conversion from your corn to ethanol. But we can think of this in sort of, it doesn't actually always have to go into like a direct energy conversion, right? As long as your units are the same. And so here we can actually talk about the efficiency of pipeline, right? And so maybe you put 100 gallons in and you only get 95 gallons out, and maybe that's because the pipeline is like leaking somewhere. And so the efficiency here, pretty easy to measure, 95 over 100. And so this is just to keep in mind that like when you, as long as the units in your numerator and denominator are the same, it doesn't always have to go through a unit of energy to do that conversion. Okay, and in this example, we can think of energy in sort of different forms. So as long as the units are the same. So here, the input for the light bulb, we're thinking about watts for electricity, but then the output, we're thinking about watts in terms of light energy output. And so you can actually do a translation of how a light bulb translates electricity into useful energy by the same sort of operation and efficiency. So this relates to that little spiel I gave about heat rates earlier, efficiency versus efficacy. And I think for a lot of what I'll be doing in this class, I'm going to be kind of using them interchangeably. But this slide is where I'm just trying to keep it straight for you guys formally, right? And so there is a difference between efficiency and efficacy. So when we think about energy efficiency, again, strictly a dimensionless number, and it's always less than 1. And that's the way that you make sure that happens, is because the units of the numerator are always the same as the units of the denominator, right? And the reason why it's always less than 1 is because of the laws of thermodynamics, you can't get more energy in, or you can't get more energy out than you put in. And that's like a nice little check to make sure that you're doing your math right. However, we will often talk about other, like an informal term of efficiency, which I should be calling efficacy, but it's so kind of prevalent in sort of the energy discourse that people kind of treat it the same. So very often we think about the ratio of the output to input, right? And so the example I was talking about before, the MMBTU to kilowatt hours or gigawatt hours, even if they don't have the same units. Okay, what's a really common example of this? Fuel efficiency, so miles per gallon. Or, these days for electric vehicles, we talk about it in terms of like kilowatt hours per miles or miles per kilowatt hour, right? So those units are not the same. And so it's not technically like a physics version of energy efficiency. So we'll call it efficacy just on this slide to make sure that you guys will keep it straight. But from sort of here on out, I'll probably just be calling it efficiency. And that is the service output versus the energy input. And again, those units don't have to be the same, and therefore that leads to numbers that can be greater than 1. Okay. So energy pathways, we're going to tie this back into our discussion about energy efficiency in a second. But this relates to some of the concepts that I've been alluding to a few times throughout the lecture, and here I'm just trying to formalize it. The primary energy is a naturally occurring resources that you can collect or extract from the environment. And so what are examples of this? So crude oil, natural gas, coal, solar. So these are all things that we are sort of directly getting from the environment. We can then take primary energy and convert it to a different form of energy. And we consider all of those intermediates between primary energy and final energy as secondary energy. So this is any resource that is basically processed through man-made activity to become, for example, an energy carrier or a different type of fuel. So electricity, right, that's the conversion of coal or natural gas into this form of energy. So that is a secondary energy. And any sort of refined liquids are also secondary energy. So examples like gasoline and diesel, which we process from crude oil, is another example of secondary energy. And then the final or delivered energy is the form of energy at the last stage being used in your energy appliance or other sort of service product that provides the actual service. And so again, when we think about the service, right, what are the things that I was saying before? Lighting, cooling, heating. So lighting comes from light bulbs, heating from a heater, cooling from an AC unit. So all of those things take electricity. And so it is the final energy is that the form of energy that those appliances need to provide you the service. Yeah, it's kind of like the second to last form of energy before it's useful to you. And then that thing gets converted to your energy service demands. And so as I go from primary energy to secondary energy to final energy, this is where that whole energy efficiency topic comes into play, because movement along your energy pathway requires conversion, and that's going to lead to efficiency losses, because you can never have sort of perfect efficiency losses, but or you cannot convert from one form of energy to another with perfect efficiency. And so when you go from a primary energy source to a final energy source, you will always have system losses. Okay, and so let's think about if we were to take this concept of energy efficiency and apply it into these sort of pathways. Yeah, so what stage of this conversion, like if I'm going from primary energy to refined fuels, or from refined fuels to useful energy, think about where in that process does it make the most sense to improve your efficiency. Okay, and so it's not actually a completely sort of straightforward answer, right? So if I were to do improvements in final to service efficiency, you actually reduce the amount of energy needed at each upstream stage. And I'm going to show a sort of really striking example of this in a second. But this would essentially be like, okay, if I were to improve the efficiency of the light bulb itself or of the like AC unit, that would be this step, right? The final service efficiency step. And because it results in larger sort of gains, you get everything along the chain is more efficient, or not more efficient, you need less of it. And so less mining and oil extraction, fewer power plants, fewer pipelines, and so on. So the gains, strictly speaking from a number standpoint, is much larger if you were to improve the light bulb compared to, in the second example, improvements of the primary to secondary efficiency. So, for example, if I were to do efficiency improvements at the coal plant or the natural gas plant, the total gains that you get from doing that are much, much smaller than improving the light bulb. But that doesn't mean that it's always better to do the light bulb. And the reason for that is that this can be centrally implemented. And so it could actually be easier to change a single station as opposed to getting everyone, everyone in the state to like change their light bulbs. And because the entities that are associated with primary to secondary efficiency improvements are, oftentimes these like corporations, they're going to act more as rational actors. And so from like a economic standpoint, oftentimes these things will happen naturally, whereas the final efficiency improvement, final to service energy efficiency improvements have to do with like behavioral changes that may have less to do with the pure economics of it. One example that I kind of always like to point out is the sort of golden success story is refrigerators. So this is the refrigerator technologies is like the thing that all other energy efficiency technologies wish they could be. Because basically what happened is that it was all really sort of low-hanging fruit with technology improvements, coupled with like standard requirements. But essentially, states and even the federal DOE basically ratcheted up these standards to make refrigerators more efficient. And it turned out it was kind of just like a win-win story because refrigerators actually ended up getting larger, or you got more space because of the way that they did a lot of those improvements, while at the same time it actually led to price drops because it turned out making the fridges more efficient was also cheaper. And so you got more energy efficiency, you got lower prices, and you got and the size of the fridges actually got bigger. And so if all sort of efficiency improvements could happen in the same way, then we would all be doing great, right? Because it's basically like a win-win-win type of scenario. And that's not always the case, unfortunately. Usually it's some kind of trade-off with costs. So efficiency of a system, when we think about pathway efficiencies, this is one nice little shortcut that I like to point out, is that everything is multiplicative. In other words, you basically to get the efficiency of entire system, you basically just need to multiply the efficiencies of each of the individual pathway efficiencies. So that the energy efficiency of the entire pathway is equal to the product of your individual thermodynamic efficiencies of each step. Okay, and to give a sort of more concrete example of this, this is a table that describes how I get from my primary energy in orange all the way to my useful energy in green. And so if I were to look at the sort of top row here, I'm going from 1 exajoule of coal. It goes through some processing, input then output. You lose a little bit of the coal, and then it goes into the coal plant. You lose a little bit more coal, and then it gets converted from coal into electricity. And so now we're in blue, which is secondary. And that's where you're going to get a lot of losses here. And so then it gets, so this is actually like electricity going to some industrial sector, I guess. And so input to a manufacturing plant, and then you get some losses when it's actually used. And so in this case, I can, this diagram gives me quite a lot of information, right? I can talk about, hey, what's the efficiency of the process from mining to input to the coal plant? Okay, it's 89% efficient, right? Because, you know, I've mined 1 exajoule worth of coal, but what goes into the power plant is 0.89 exajoules worth of coal. And so the efficiency right there is 11%, or sorry, 89% with, you know, 11% losses. And I can calculate the individual efficiencies. And so if it was like 99% here, and then from here to here, it'd be, you know, approximately 10%. And then from here to here, 0.28 of 0.89, that's what, like maybe 30%. So if I were to take all of those efficiencies and multiply them together, you'd end up getting sort of ultimately this pathway efficiency. And that's what the sort of last slide was describing. So there's a similar type of table that's going to appear on the homework, and so that's kind of how you'll interpret this table in terms of the relative efficiencies and energy use in each step in the table. So one thing that I like commonly hear, and this, I think this is a sort of nice demonstration of this concept of energy use across the whole pathway, is about the efficiency of an electric vehicle versus a gasoline vehicle. And oftentimes what we're talking about, right, is like how many miles can I get out of like a unit of gasoline in a gas car versus how many miles can I get out of a kilowatt hour in an electric car. And indeed, you can actually see that it's quite a bit higher in electric vehicles. And so here, okay, this is a gas car or internal combustion engine vehicle, and you get 7.58 exajoules of petroleum, and you get 1 exajoule of sort of useful energy out of it. So it's like 13% efficiency. That's not, you know, directly the efficiency of the engine. There are some other things happening in between, but compare that to an electric vehicle where the electricity input is 2.53 exajoules, and then you get this 1 exajoule useful out of it. And what you'll see is that, right, the electric vehicle is like 3 times more efficient than the gas car. And I guess that's one way of looking at it when we're thinking about the fuel consumption at the vehicle end. But to me, that's always seems a little bit kind of disingenuous, because you're comparing like a post-combustion process with a pre-combustion process, right? And so if I were to actually look at the full sort of life cycle, just in terms of efficiency, right? I'm not saying electric vehicles are bad or anything. You'll actually see that from the primary energy, it's 8.33 exajoules of crude oil to get the same amount of useful energy, whereas it's 10.1 exajoules of coal or 9.7 exajoules of natural gas. And I think these, personally, I think these numbers might be like slightly off. But at the end of the day, it ends up being somewhat close, and really kind of what you're comparing is across the full life cycle is you're doing a more fair comparison, where it's like, what's the efficiency of the combustion engine versus the efficiency of like a turbine in a power plant, right? Which is the thing that's actually burning the fuel. And so I think this gives a sort of nice view of the sort of full efficiency across the pathway from primary energy to useful energy. Okay. So the last thing that we'll be talking about today is back to this concept of, actually, let me just go back, the improvements in efficiency and their impact on the sort of full pathway efficiency. So now that you've seen kind of what it means to go from primary energy to all the way down the pathway to their useful energy, now let's take a look at this concept of, hey, what happens if I were to improve the efficiency of this step to this step versus this step to this step? And so the example that we're going to look at is going all the way from a power plant to the light energy that you'd get out of a light bulb. So let's say you need, quote unquote, sort of 1 unit of energy coming out of your light bulb as kind of the final sort of useful service metric. Okay, well, if I go all the way back to the power plant, I'm going to need 320 units of that energy, right? And so what happens is that primary energy, whether it's natural gas or coal, it's going to get burned. And that's usually where sort of the largest set of losses is occurring. You're going to get 65%, which is like wasted heat energy. And then 112 of that is going to be electricity. Okay, and going from the power plant, you're going to do your step-up transformers through your transmission system, step down through your distribution lines, and those processes you're going to lose a little bit, so 5% and 5%. And then that's going to go all the way into your house, and then through your wiring, you're going to lose a little bit, and then in the lamp. Okay, so this is an example of, for example, an incandescent light bulb, where you put a lot of electricity into it, and you lose a lot of heat. And so I don't know if you guys remember, but back when we used to have lots of incandescent light bulbs, one of the big features of these light bulbs is they get pretty hot, and that heat is basically just wasted energy. And so if we think of what we want as just light and not the heat, then you get a huge amount of losses in that light bulb, so 98%. So actually that's even bigger than what you're losing in the fuel to electricity conversion. Okay, and so in this whole process, to get my one useful unit of energy, I need 320 units of my primary fuel. So now let's think about improving the light bulb and then improving the power plant. Okay, so this is always, I think, kind of like a striking example. So in this case, so you'll notice here, this is now 50%. And in the previous one, it was 65%. So we're losing 65% of the energy here. But now we've improved the power plant so that you only lose 50%. It's a 15% improvement in the overall efficiency of the power plant. And so instead of 320 units of energy to get that one useful guy out, we only need 224. Right, and so you're getting like a 30% reduction in primary energy usage. And so that whole process, by improving the power plant, I'm going to save 30% of the energy sort of down the line. Okay, now let's see what happens if we improve the light bulb. So let's say I were to get a slightly more efficient incandescent light bulb, or a different sort of technology light bulb. And so where this number used to be, right, 98% in our original example, so you only get 2% of useful stuff out of it. In this case, it go from 98% to 90%. And so I get 10% or 5 times more out of a single light bulb. Okay, so see what happens here. The efficiency sort of trickles all the way upstream from the production. And so in order to get that one single unit of useful light, I only need 64 units of your original primary energy. And so, like I was saying before, this type of improvement, because it affects everything upstream of it, efficiency improvements closer to your service, useful, or final energy stages is always gonna, kind of pound for pound be a lot more effective in reducing your ultimate energy use. And that's because of the way the pathway efficiency works, right? And so again, these things oftentimes are kind of more heavily promoted or more impactful when you have like policies that can do sort of downstream things, but are oftentimes a lot harder because you're usually asking like customers to change technology or behavior as opposed to like a centralized entity, and so that spells some of the differences in why, even though your top example doesn't get you as much as the bottom one, like it can oftentimes be easier to do this top type of thing rather than the bottom one. Okay, and so yeah, that's the last sort of bit we're covering on energy efficiency today. So we'll end here, and yeah, I'll see all of you guys on Wednesday. I'll stick around for a couple of minutes if anyone has any questions or concerns, not only about this topic that we were talking about today, but if there are any sort of overall like course things, I'm happy to chat about that. And so otherwise, I will see you guys in 2 days.